Good morning, everyone. We are from Thermodynamics class 01, and today we're going to present about Brayton cycle. And our group consisted of me, Yomi, Gita, Pertiwi, with the student ID number of 131246163. And then there's Nazya Rezyarifin with the student ID number 131243133, and Galvandi Ibrahim 131245157. Okay, next. Okay, so what is Brayton cycle? Brayton cycle is basically a cycle that describes how gas turbine operate. Brayton cycle is also a cycle that extract energy from flowing air and fuel to generate useful work which can be used to develop power. Next. Alright, so the schematics of Brayton cycle, as you can see from the closed cycle and also the open cycle. First, air and fuel went inside into the compressor, and then it goes through the heat exchanger or combustion chamber, and then went through a turbine, and lastly it went to heat exchanger. And you can see from the PF and TS diagram where during the when during the combustion when inside the compressor, the it's basically going through entropy, and then inside the turbine, it also went through entropy. And for and when it through and then when it went through the heat exchanger, it goes through the same pressure from inlet and outlet. Next.
So these are the differences between power cycles, which consists of diesel, Atkinson, and Brayton. So you can see from the table that mostly their engine types are piston, whereas for Brayton itself, it's mostly contains of turbine. And also, Brayton itself has constant pressure, continuous combustion, continuous flow process, no phase change, and their best application is mostly used on jet engines. And for the formulas itself, we have thermal efficiency, the backward ratio, the thermal efficiency for cold air standard basis, and the regenerator effectiveness for the regenerative gas turbine cycle. So the backward ratio itself is a measure of the energy used by compressor or pump in a thermal cycle compared to the total energy produced by the turbines. And these are the applications of the Brayton cycle, where it is mostly used on LNG, jet engines, and turbines. And the schematics here is used on LNG.
Okay, so for the problem example, I think I will share my screen first.
Okay, now moving on to the problem example. Here the question states that air enters the compressor of an ideal air standard Brayton cycle. This is important as we can assume that the processes at the turbine and compressor are isentropic. And we can also use the air as an ideal gas model. And this is the data that they gave us. And we're being asked to find the thermal efficiency, backward ratio, and the net power developed. For the net power developed in SW in kilowatts. And this is the schematics. As mentioned by my friend Yomi earlier, this is going to be the TS diagram for a Brayton cycle. This is going to be a straight line because it's an isentropic process for the turbine and the compressor. And this is schematics that was also explained by my friend earlier. And here are the data that they gave us for each states. T3 they gave us the temperature already. T1 they also already gave us the temperature. Okay, and for the assumptions that we need to make, we need to assume that it's control volume and it's at steady state, and the turbine and compressor processes are isentropic. This is also because of the statement in the question, where it's an ideal Brayton cycle. And there are no pressure drops for flow through the heat exchangers. And this is also the requirement for a Brayton cycle. And the kinetic and potential energy effects are negligible as usual. And the working fluid is air modeled as an ideal gas. So the air is considered an ideal gas, so we can use the ideal gas relations. Okay, so first, because it's asking us to find the thermal efficiency, backwork ratio, and the net power. The thermal efficiency and the backwork ratio requires us to find the enthalpy at each state. Okay, I'm gonna explain the formula first. The initial formula for thermal efficiency is like this, but we can simplify it to be like this using the energy balance equation at steady state, because we can assume that dE over dt is equal to 0, kinetic energy and potential energy is neglected, and in an ideal gas, an ideal Brayton cycle is going to be an isentropic process, which means that it needs to be adiabatic as well. Hence why there's not going to be any heat transfer in the turbine and the compressor. So the only thing that's left is going to be the enthalpy. Okay, same thing here, but instead of there's no heat transfer, there's not going to be any work done in the heat exchangers, so that we can simplify it into H3 and H2. So all we need to find to answer all of these questions is to find the enthalpy at each state of the Brayton cycle. So first, because at state 1 we're already given the temperature directly, we can just look at the table and we will get the value of H1 without having to interpolate at all. And meanwhile we're looking at the table, we can also find the PR1, which will be used to find the PR2 using the isentropic relation for air. We can find that PR2 is equal to 13.86, and from that we can interpolate using the same table, table 822, to get the value for H2. And for the state at temperature at 3, because we were already given the temperature, we can just look at the table directly and we will get the value of H3. Same thing that we did for state 1, we will also find the PR3 and use this to find the PR4 for state 4, and we will use this value to interpolate using the table to find the enthalpy at 4. And they will give us all of the information that we need to answer part A and part B. As I mentioned earlier, we just need to substitute the value that we have, and we will get that the thermal efficiency is 45.7%. Same thing with the backwork ratio. This is the work at the compressor and the work at the turbine. We can see that the backwork ratio is 39.6%, only using the value of enthalpy. Now for part C, we will need the mass flow rate. But because the question only gave us the volumetric flow rate, we need to do some calculations to find the mass flow rate. First, we can see that the mass flow rate is going to be AV. A is the cross-sectional area. V is going to be the speed, and V1 is going to be the specific volume. Because the value for the top side is meter squared multiplied by meter per second, and the bottom part is going to be meter cubed per kilogram. Cancel. It's going to be kilogram per second, which will give us the mass flow rate. Hence why the formula is like that for this. And using the ideal gas relation, this one, the PV equal to R over MRT, and using the relation that we mentioned earlier, we can rearrange it to be like this. And because we already have the values for all of this, we will get that this is going to be, the mass flow rate is going to be 5.807 kilogram per second. Also, this thing is equal to the volumetric flow rate, which was given in the question, 5 meter cube per second. Okay, now that we get the mass flow rate, we just need to substitute it to the the formula for the net work cycle, and we'll get that as 1481 kilowatts. Okay, that's it from our group. Thank you.